So in this lecture we're finally ready to define a Poisson point process in general. So we talked a bit about point measures before, so for this we needed S, a space that we're going to restrict it a little bit. Let's call it, let's assume it's a metric space that is locally compact and polish. Let's just make our life easy. Okay, so the examples you should keep in mind are always like R or R plus or RD, a manifold. So keeps reasonable things in mind, but it could be something more general, like maybe a fractal set. Infinite dimensions are going to be limited somehow by this local compactness. But anyway, we have a very general setup, and you can think of S as the place where the points are going to fall. So we've defined in the last class the space gamma of the point measures here, so this belongs to gamma, and we also defined sigma algebra on that space, so that we can talk about random elements of gamma, which are the random point measures. So the Poisson point process is going to be a random point measure. But before that, we have to fix sigma, a measure. Sigma is going to be terrible. Let's use nu, maybe. So nu is a measure on S, which is sigma finite. So we don't want it called sigma because sigma being sigma finite is a bit ugly. So we have a measure down on S that's sigma finite, and we call this intensity. So what this measures essentially is like if we have the space S, mu is a measure here, maybe it gives more measure to this region here, and this region is very low measure, so it means there will be more points here, and here it's going to be more sparse. So lots of points where the measure is high. So this is the intuition behind this intensity measure. It gives how intense the point measures, the Poisson point process is going to be in each region. Now we're ready to define. So we say that M is a Poisson point process, and it's very common to abbreviate as PPP, a Poisson point process on S with intensity nu if for every B1, B2, Bn in A, and I forgot to recall that A is the sigma algebra of a Borel sigma algebra associated with S. So for every finite collection of B in A which is disjoint, so mutually disjoint, then the vector m of B1, we saw that these are random variables, m of Bn, so these have independent coordinates. So let's remove the vector notation, just say that these random variables are independent. And the distribution of MBI is a Poisson random variable. And what's the parameter of the Poisson? It's going to be exactly nu of Bi. That's why if a region has larger nu, it will have more points, because the parameter of the Poisson process is going to be higher, and you're going to get more points. So this is the definition of a Poisson point process. If you take your space S and you have disjoint regions, then the number of points falling in each region is Poisson distributed. The parameter is the measure of each region according to nu, and what happens in each region, being disjoint of course, is independent. But that's just a hopeful definition, right? We don't even know if such a thing exists. So now we're gonna state a theorem that says that for every new sigma finite, this Poisson point process with intensity measure nu exists. And here goes the proof. So we're gonna do a constructive proof. So we take the nu, and we know that it's sigma finite. So in particular, there exists a collection of boxes, of sets, sorry, A1, A2, and so on, potentially countably many of them, with nu of AI almost always finite, and AI disjoint, and the union of AI is S. So you can partition the space S with sets that have finite measure. The advantage of this is that, you see here, I didn't say what happens when this measure is infinite, but you should think of that as the Poisson variable with parameter infinite is equal to infinite almost surely. Here we are first slicing the space to get finite things so that our Poisson variables make more sense. So now we have this partition of S into finite pieces, finitely measured pieces, and we can already define xi to be independent with xi distributed as Poisson with parameter nu of AI. So it's exactly what our definition asks us. Of course, the definition limits itself to finite sets, not infinite, but it's the natural extension, right? If you have an infinite collection, they're disjoint, so we should put independent Poisson variables with the right intensity on them. But this only tells us how many of them, how many points you find in each region. It doesn't tell where they are. So for this, we're going to define Yij. So now not only you have this infinite collection of x, but we have y's, which are also independent. And Yij has a distribution that is nu conditioned on AI. So nu of something intersected with AI divided by nu of AI. So this is a probability measure. So you can define it more carefully if you want, but I think it's clear enough. This is a probability measure that has support on AI. It's essentially nu conditioned on AI. Now, y's, you see, they have a distribution that depends only on I. Fixed I, these y's, j's are IID. So what we do now is we define the point measure M. So recall that M should be a sum of deltas. To be a point measure, it should look something like this. But now the sum is going to be a double sum because we have i's and j's. So I is going to be any I. We're summing over all this. We are doing something in each of these regions, for every region. Now for given a region, we are going to sum j only from 1 until xi. So if we have 3 points, this is determined by the fact that xi equals 3. And you're going to only sum j from 1 to x, to 3, sorry, to xi, which is 3. And the delta is on yij. So the y's, the x's are in z plus, and the y's are in s, or in ai actually. So we're going to sum deltas of yij. So this is a construction. It will look like a point measure. Good. But there is no reason why this satisfies this hypothesis. If we choose B to be exactly our ace, then we are in luck, and our construction gives automatically the Poisson hypothesis. But now what we need to do is to take this and prove the hypothesis for arbitrary BIs. Caetano, papai tá dando aula. So here we are gonna have to break the set A. Here we have A1, A2, and so on. And we also have the sets B, which have in principle nothing to do with A's. So I'm drawing them here. This is B1 up to Bn. And what we have to prove is that the number of points in Bi are independent and Poisson distributed, because we know this for A's, not for B yet. So what we do first is define random variables Z, I, L, which is the number of points that fall inside AI intersected with BL. So here I is anything, but L is just going from 1 to n. So it's like we are looking into these pieces here. This piece, this piece, this piece. So we split by both A's and B's. Now if we draw this as a kind of matrix, so we have here Z11, Z12 until Z1 n, then Z21, Z22 until Z2n, and it continues forever, potentially. Now what we know? We know that fixed A, what happens inside the slice A, so what happens here is independent of all the other A's. That's by construction. So what happens in this green region is independent of all the other, what happens in all the other A's. So it means that this are independent vectors. This is independent from this, is independent from this, and so on and so forth. Now I ask myself what happens inside, because it's not clear that this is independent of this. We know that this is independent of this is independent. But what about these ones? So let's focus on one of these vectors, right? So fixed I, we can have n plus 1 possibilities. So either fixed I and some point y, I, j, right? This is a point in AI. It has several possibilities. Y, I, j could belong to B1, or it could belong to B2, or it could belong to Bn, but there's still one possibility that it belongs to B tilde, which is the complement, like A, I minus all these B's. So one of these things have to happen. How is this being chosen? So this is chosen with probability nu of B1 over nu of A. Sorry, B1 inter A1 over nu AI, sorry, over nu of AI. The last one is chosen with nu of Bn inter AI over nu of AI. And the last one is chosen with nu of B tilde inter AI, we don't even have to intersect now, over nu of AI. So here we have some probabilities, so these numbers that sum up to 1, non-negative numbers that sum up to 1, so they're probabilities that select each point in our Poisson random variable x to color it in different colors. So in the end we are taking xi, which is a Poisson random variable with parameter nu of ai, and it's being colored from 1 up to n plus 1 with this distribution that I'm gonna call, I don't know, mu. It's some measure on the space, on this finite space here. So what happens with a Poisson random variable, that you, for every point there, you select a color independently with a given distribution. It will give rise to zi1 up to zin and zi tilde, which are independent, and zij has distribution Poisson nu of ai intersected with pj. So that's what we obtain. So by the thinning lemma, we see that this is also independent. So in the end, once we sliced the space in all the i's and l's, we got everything independent. This is independent of this, which is independent of this, which is independent of this. Every slice that you obtain is independent, and they all have distribution given by a Poisson random variable with parameter nu of the intersection, so nu of the region that that slice corresponds to. So why is this interesting? Because now that we sliced, we can join. And the way we want to join is by not looking at these groups that I drew here before, because these black groups were the ones used to define the Poisson point process, but the red groups are the ones that we need to use to prove that it's a Poisson point process, because the sum here is equal to the number of points in B1, and the sum here is equal to the number of points in Bm, and this is what we want to show, that so this vector we want to show that it's independent and Poisson distributed. The independence of this vector mb1 to mbn, so mb1 to mbn are independent because the zij for every I and j is independent, and moreover m of b l is equal to the sum of these independent variables here, z I l for I bigger or equal to 1. So we know that this vector here is an independent vector, because every entry in this matrix is independent. Now, why it has the right distribution? What is a distribution of a sum of Poisson random variables? It's still Poisson. So this is still distributed as, so a sum of Poisson independent random variables, still Poisson, and the intensity, the parameter here, is the sum over I of the intensity of Zi. So let me drag it down a little bit. So this is the sum over I of the intensity of this guy. What's the intensity of this guy? Is nu of AI BL. But nu is a measure, so the sum of these independent sets is just the measure of the union. And what's the union here? Is just AIs, they exhaust the whole space, so this is just BL. So what we have proved is that for every BL, B1 to Bn, the vector M of B1, M of Bn is independent, and it has a Poisson distribution with the measure of BL, which is exactly what we need to say that something is a Poisson point process with intensity measure nu. Now, one thing that you should be asking yourself, and it's very important, is why on earth is this a random point measure at all? Why is this even measurable? So the reason is the same. You see here that this is what we have to show that is measurable, right? M of BL. And we're showing that it's a sum of random variables. So this is definitely a random variable. And this is true for every B. For every B, we find it's going to be a sum like that. So there is no secret here. This is going to be measurable a posteriori. So there you go. We have a way to construct this Poisson point process. It works in any space. It doesn't have to be the real line. Now we can, for example, take the plane, and we have this Poisson point process in the plane. Now, one thing you might be asking, besides the Poisson distribution that appears everywhere, why is this called Poisson process? Is it related at all to the Poisson process that we already defined on the real line? So on the real line, fixed parameter rate lambda bigger than 0, so this is just a real number, we can take nu to be lambda times the Lebesgue measure. So let's consider R plus here. And we can define the Poisson point process on R plus with this intensity measure nu. So it's going to give us some points, right? Now, two important observations. First, the number of points falling in a collection of intervals like this. So if this is B1 and this is Bn, the number of points in B1, number of points in Bn is independent, and the number of points in BL is distributed as Poisson times lambda times the Lebesgue measure of BL, that I'm going to denote like this, loose notation. This is exactly the distribution of points that we observed for our other construction of the Poisson point process using exponential jumps. So if you remember the construction we had before, we proved exactly this statement. So this is a nice observation. Another observation is that the set D that gives us all the vectors M of B1, M of Bn belonging to A. This was a pi system that was sufficient to show uniqueness. So the fact that one holds gives us that the measure we obtained before, so before we had only these TIs, right? T1 smaller than T2, smaller than T3, and so on. They were defined as Ti is the sum of xj, where xj were independent exponential lambda. So you see that we had this construction of the Poisson process in the line that had nothing to do with the construction above, and we can use this to define M equals sum of delta Ti. We're just making a point process that gives a delta in each of these points, in each of these occurrences. This will have the same property 1, and by the observation 2, this is the same distribution as the process that we constructed in a weird way here. So we can take the real line, for example. If you want to simulate a Poisson process in the line, you can do sums of exponentials like this. But another thing you can do is to fix, it's actually more parallelizable. You can take for each of these intervals a Poisson lambda. So for this, for this, for this, for this. So imagine that here we have Poisson lambda equals 5. So what you do is you pick 5 uniform points in this interval with the uniform distribution independently from each other. Here, if this is equal to 2, you take 2 points. If this is equal to 0, you take 0 points. So this is a simulation that's going to give us the same distribution as if we were summing exponentials. So this is a brief introduction to Poisson point process, but you have the construction, you have the equivalence with what we saw in the line, and it's much more general. It works on very general metric spaces. And in the exercises, I'm going to give you some nice examples where you can do some calculations above. So see you. Bye-bye.